Good day, class. My name is Uduak Aletan. I'm your facilitator for the course Bio 216, Chemistry of Carbohydrates, Lipids, and Nucleic Acids. The title of the course must have sounded or must sound loud or fearful, but really there's nothing to be afraid of. I know that by the time we continue through before we finish this course, you will have no reason to fear again. So let's start. Our first class is on carbohydrates. I want us to journey together. Enjoy the trip. So let's start. Unit 1, carbohydrates, physical properties and functions. When we talk about carbohydrates, what really enters your mind? You must have eaten a plate of fried plantain at one time or the other, boiled yam with oil, which I love so much, or even bread and butter. All these things are carbohydrates in one form or the other. Now, what is carbohydrates? Carbohydrate describes a group of organic compounds ranging from simple sugars like the glucose they give you to lick when you're doing sports, through polysaccharides, which form some of the important structures in the biosphere. Now, at the end of this class, you should be able to define carbohydrates, list the major classes of carbohydrates, list the properties of carbohydrates, highlight different functions stroke roles played by carbohydrates in living system, and explain the stereochemistry of carbohydrates. So let's start. Definition of carbohydrates. Like I said, carbohydrates can be defined as polyhydroxy aldehydes or ketones. Polyhydroxy aldehydes or ketones. Or any substance that yields these compounds on hydrolysis. When we talk about polyhydroxy, that means it contains a lot of hydroxy groups, or any compound that when it is broken down yields this polyhydroxy of aldehydes or ketones, can be comfortably called carbohydrates. I know that aldehydes and ketones are not strange words to you, because you must have done them, you must have met them in your secondary school chemistry. Now, the general formula for carbohydrates is this: CH2OH with all brackets N. But not all things we call carbohydrates fit into this group. This may be okay for glucose, sucrose, even starch. But there are so many things that are carbohydrates which do not fit into this group because they may contain nitrogen, phosphorus, or sulfur, or some are even deoxy sugars. As you can see, there's no nitrogen here, there's no phosphorus or sulfur. So this formula is not and will not fit, will not be okay for all carbohydrates. So now let's classify carbohydrates. Carbohydrates can be classified into three major groups: monosaccharides, oligosaccharides, and polysaccharides. Monosaccharides, you can see each of these words I've used have a root word, saccharide. And saccharide is from a Greek word saccharon, which means sugar. So when you say monosaccharide, that means one. Of course, you know that mono means one sugar. Oligo is also a word that means few sugar, and poly, many sugar. So depending on the number of sugars present in a carbohydrate, it can be classified as mono, oligo, or polysaccharide. Now, what are the functions of carbohydrates? Carbohydrate performs a lot of functions in our environment and even in us. First of all, the most important function of carbohydrates is that carbohydrate is its primary role as a nutrient. When you eat to get that nutrient. And when whatever you eat that contains carbohydrate, your body will break it down to get what it needs or what it can use. And the most important carbohydrate to the body is glucose. As a nutrient, glucose is the most important carbohydrate as a nutrient to the body, because that's the one the body can easily use to work. Then carbohydrate also functions as an energy, as an energy store. We have in animals, carbohydrates is stored as glycogen, whereas in plants it is stored as cellulose. So we can use a carbohydrate to store. Carbohydrate stores energy for us, so that when we need them, they will be broken down and we'll use them. Carbohydrate also serves as a structural component of cells. It serves as a structural component of cells. You must have heard of the word chitin. Chitin is found in insects, and then cellulose found in plants. Carbohydrate serves as a structural component in insects and in plants. That's why when you try to kill an ant, you see that thick, hard covering on it. Then carbohydrate also serves as a component of glycoproteins. And carbohydrate also functions as an antigenic determinant of blood group. Now look at this insect. When you look at this insect, you see this thick black covering on it. This is what is known as the chitin. This is made of carbohydrates. You see, it is helping to protect and to make this insect firm. Then also, another function of carbohydrate is that it lubricates our joints. Imagine how it will sound when you are walking and your bone is cracked scratching, your bones are scratching one another. In order not for this not to happen, the body has a carbohydrate in the joint called hyaluronic acid. So this carbohydrate helps to lubricate the joints, just like your engine oil lubricates your car or your generator. Also, I mentioned carbohydrates for blood group determinants. We have different blood groups. We have blood group O, A, B, B, and A. These blood groups, what differentiates them from one another are the carbohydrates they have on their surfaces, on the surface of the cell. So for somebody who has O positive, it does not have, the blood cell of such a person does not have these carbohydrates on the surface. If you have AB, the blood cell has carbohydrate A and carbohydrate B on the surface of the cell. And you see, it differentiates it from O, differentiates it from AB, from B, and differentiates it from A. So this is another function of carbohydrate. Carbohydrates, e.g. galactose and fructose, also function as antigenic determinants of blood group system. Now let's look at the physical properties of carbohydrates. Carbohydrates, for example, monosaccharide, which we know is soluble in water. That's why when you put glucose in water, it dissolves. It is soluble in water, but insoluble in chloroform. If at times when you put sugar, this sugar we used to drink in sucrose in water, you also see it dissolves because some of those carbohydrates are soluble in water, but polysaccharides are not soluble in water. That's why when you put starch in water, you will see it there. You will still see the white particles of the starch because they are not soluble in water. Carbohydrates are solid at room temperature. That's why we see starch solid, sugar, glucose solid, sucrose solid. Carbohydrates, most monosaccharides and disaccharides are sweet. Glucose is sweet. Sucrose is sweet. And what makes honey sweet is also the carbohydrates, monosaccharides in it. The fructose also in honey. Carbohydrates are, example, monosaccharides are colorless crystalline solids. If you look at sugar, if you pick a piece of glucose, if you pick a crystal of glucose, you will see it is colorless crystalline solid. Then monosaccharides, disaccharides, and polysaccharides are odorless. These are the properties of carbohydrates. Now look at this is our glucose. If you pick one piece of it now, you see it. Well, just one crystal. I'm sorry, not one piece. One crystal, you will see, you will look at it, just like you can pick a crystal of table salt. Now let's look at the stereochemistry of carbohydrates. Carbohydrates as organic compounds exhibit stereoisomerism. And what do we mean by stereoisomerism? If you look at stereoisomerism, you see one word there. Isomer. Isomer. What are isomers? From our chemistry, organic chemistry, we will know that isomers are molecules or polyatomic ions with identical molecular formula, but different arrangement of atoms in space. By the time we go further, and you will see the molecule, you will see the formula of glucose and fructose. You see that they are both the same, C6H12O6. But when you write the formula, you will see that the arrangement of the OH and the arrangement of the O's and the H attached to the C's to form these compounds are different. And because they are different, we say they are isomers. So when we talk about stereoisomers, we're talking about organic compounds that have different molecules in which the order of bonding is the same, but the spatial arrangements among the atoms are different. Yeah, look at this now. There are different forms of stereoisomerism. The first one we're going to look at is what we have here now. This is glucose, and this is another glucose. These two molecules are mirror images of one another, of each other. You know how you feel, how you are when you look at a mirror. Your right hand in the mirror becomes your left hand in real life, and your left hand becomes your right hand. That's how it is here now. You see, all the things that were on this side have gone to this side, and all the things that were on this other side have gone to this side. So you see, this is still glucose, but they have been arranged differently to become mirror images of one another. So for this type of isomerism, we call enantiomers. Enantiomers, they are stereoisomers that are non-superimposable. They are non-superimposable mirror images of each other. What do we mean by non-superimposable? I drew my hands here to show you what we mean. See, my left hand and my right hand, they are exactly the same. They are mirror images of each other. But if I try to put my right hand on top of my left hand like I tried here, my thumb will not be. My thumb will be, one thumb will be on this side and the other thumb will be on this side. The thumb will not be on top of the other. And that's why when I wear my shoe, I cannot wear my right shoe on my left foot. And I cannot on my left foot. And I can also not wear my left foot on my left shoe on my right foot, because my feet are also, though mirror images, are non-superimposable. Another type of isomerism, and what brings about isomerism, this stereoisomerism, is what is the chirality of carbon. You see, this carbon is a chiral carbon. Why? Because it has 4 different groups attached to it. You see, a hydrogen is attached to it, a fluorine atom is attached to it, a bromine atom, and of course a hydrogen atom. So there are 4 different atoms. So it is also called an asymmetric atom. This is what brings about this stereoisomerism we're talking about in most of these organic compounds. Now, this is another type of stereoisomerism. This is called distereoisomerism. You see, they are almost the same, but they are not mirror images of one another, of each other. You see, there are 2. Look at these 2 and look at this. And because of these differences, we have, this is now glucose and this is maltose. When stereoisomers that are not mirror images of each other, I'm sorry, you see what we have here? They are stereoisomers, but they are not mirror images of each other. Another distereoisomers is what we call epimers. Epimers are also stereoisomers, like I said, but their difference is just on one carbon. At one point, on one carbon. This is glucose, and this is a friend of glucose known as galactose, or you can call it a cousin of glucose known as galactose. And this is another cousin of glucose known as mannose. Three of them are isomers in that they contain the same number of atoms. But now the arrangement is different. This glucose is different from galactose because of a difference in carbon 4. See the arrangement of carbon 4 here and see what has happened here. Just because of this difference, this glucose can no longer be a glucose, it became a galactose. So we say glucose and galactose are epimer, they are carbon 4 epimers. That means the only difference in them is on carbon 4. And look at this again, you find out that this is also almost exactly, except for carbon 2. So this is mannose. Mannose and glucose are carbon 2 epimers. But if you look well at mannose and galactose, you will see that they differ in more than 1 point of carbon. So they are not epimers of each other. But this and glucose are epimers, carbon 2 epimers. Galactose and glucose are carbon 4 epimers. So epimers only differ in the configuration about only one asymmetric carbon. So talking about asymmetric carbon, look at this. How many asymmetric carbons do we have in glucose? You see this glucose here has how many? You see, it's attached to hydrogen here, OH here, and a different group here, and another different group. So this is 1. So this is an asymmetric carbon, same as this, and this. But look at this carbon 6 now. You find out that this carbon 6 has a carbon, these 2 hydrogens, one is attached here and one is attached here. So because it has 2 hydrogens, that means the same atom appearing twice, it cannot be said to be an asymmetric carbon. Now, the last type of isomerism we'll talk about for this class is known as anomerism. And anomerism only occurs in cyclic compounds. This is glucose. At times, glucose decides to collabo. The atoms in glucose decide to collabo. You see this carbon 1 decides to collabo with carbon 5 to form a cyclic compound. When carbon 1 collabos with carbon 5 to form a cyclic compound, you have something like this. The hydrogen atoms are still arranged as they are, but you see, the one in carbon 1 has joined with carbon 5. So we have what we call as a cyclic glucose. So when this occurs, the hydroxy ion on carbon 1 may either go up, like it is here, or come down. When it goes up, it is called a beta anomer. When it comes down, it is called an alpha anomer. So this glucose, which is now cyclic, is now alpha glucose. And this one is now beta glucose. But because, remember, this glucose was a D-glucose before it became an anomer. It is alpha D glucose. And this is alpha beta D glucose. Glucopyranose. In our next class, you will see why we call this pyranose. I hope we have been able to make meaning of this unit. So we can round up by saying we have been able to define carbohydrates, we have looked at the functions and properties, and of course, we have looked at stereoisomerism in carbohydrates. Thank you for listening.